In this video, we continue with chapter 6. We will cover chapter 6.5, all about applications of linear transformations. So our learning objectives for this set of 2 videos are to identify linear transformations defined by reflections, expansions, contractions, or shears in R2. And our second learning objective that you'll see in the second video is to use a linear transformation to rotate a figure in R3. So here we have some of the elementary matrices that we use for linear transformations in R2, and we're going to work through examples using these kinds of linear matrix transformations. So the first example here is if we want to reflect in the y-axis. So notice the change between the identity matrix and the reflection in the y-axis is that we have a -1 in the first entry. And then similarly, to reflect in the x-axis, we have a -1 in the second row of the identity matrix. If we want to reflect about the line y equals x, notice we have the diagonals flipped from the identity matrix, and that's going to flip our x and y values across that line y equals x. And then for horizontal expansion or contraction, that's when we have constant k in the first entry of the identity matrix, and we still have 0, 1 in the second row of the identity matrix. If k is greater than 1, then we're going to expand horizontally. If k is between 0 and 1, then we're going to contract horizontally. And remember, a negative would involve a flip or a reflection like we saw up in that first matrix, the reflection about the y-axis. And then if you want to expand vertically, you put a constant in row 2, column 2 of our matrix here. And so again, a constant greater than 1 is going to be vertical expansion, and a constant between 0 and 1 is going to shrink or contract our geometric object or whatever we're working with. And then the last examples that we're going to see are what are known as shears. So in a horizontal shear, you have the identity matrix with the k in the row 1, column 2 entry. And we'll talk more about it, but a shear is essentially a transformation where you're transforming the points along a given line. It's sort of like a proportional tilt of geometric, I said image, but of a geometric object. In 2D, it looks like an image, but in 3D, we'll see you can do shears there as well. So shearing a figure isn't going to change its area. It's just kind of like if you knocked over a wall at an angle or something. So we'll see some examples of that. And then a vertical shear, which tilts in the vertical direction, has the identity matrix, but in row 2, column 1, you've got a constant k there. So let's take a look at reflections. So the first example, we are reflecting about the y-axis here. So you can see our point changes from xy to -xy. And so that matches what we saw in that first matrix. The second reflection option is reflection about the x-axis. So you can see here we get x -y in our reflection. And so that calculation matches what we saw in the second reflection matrix. Let me write that out for us here. So that second reflection matrix was 1, 0, 0, -1. And if you multiply that by x and y, you see this is going to give you x and -y. And then similarly, for the first visual we have here, our reflection matrix for reflection about the y-axis is -1, 0, 0, 1. And if you multiply that by xy, that gives you the -xy that we got here. Our third reflection over here is about the line y equals x. So that's where our matrix flips the diagonals. So that is the reflection matrix 0, 1, 1, 0. And if you multiply that by xy, you can see that gives you yx. And so that's how we got this flip over here. All right, expansions and contractions, this is where we multiply by a constant. So in our first graph here, we're looking at a contraction. So the constant K is less than 1. So you see Kx moves the horizontal value closer to the origin. So we say that's a contraction horizontally. If we're expanding horizontally, we see Kx, now that K is greater than 1, stretches our vector out in the horizontal direction. And then similarly, for contraction in the vertical direction, if Ky, where K is between 0 and 1, is our change, then we sort of shrink in the vertical direction. And if K is greater than 1, Ky expands in the vertical direction, or extends in the vertical direction. So here's a visual of shears. So a shear is a transformation in which all the points along a given line L remain fixed, while other points are shifted parallel to L by a distance proportional to their perpendicular distance from L. So shearing a plane figure does not change its area. You can see that if you took the triangle out of this rectangle and then moved it over to the end, that's just what we've got right here with our shear. The shear can also be generalized into 3 dimensions in terms of thinking about planes being transformed instead of lines being transformed. Here are examples of horizontal shears and vertical shears. So the matrix we use for the shear is 1, 0, K1, and that's equivalent to the linear transformation x comma y plus kx. And you can see that if you multiply out our matrix here. So in this example, K is 2. So we see this is x plus 2y comma y. And so you can see the change here between the point xy over to x plus 2y comma y. And you can see how that kind of affects the whole line down here in the quadrant 3 space as well. Here's an example of a vertical shear on the right. So here our transformation matrix becomes x plus ky in the first entry and y in the second entry. So here we've got x, y is shifted to x and y plus 2x. And so we see here in here, it looks like I've got these examples in the wrong spot. So I'm going to flip flop. I mixed up my matrix for vertical shear and horizontal shear. So I'm going to pause and adjust that. Okay, so I have flip flopped the matrices. Be on the lookout in your textbook. It looks like they might be in the wrong order because I pasted these images from the textbook. So if you're reading section 6.5, just be aware, I think the matrices are in the wrong order in there. So here's our vertical shear matrix over on the right, where the second entry is the y plus kx that we see here. Okay, in these next slides, we have images of how reflections look in R2. So imagine we're starting with this letter F, and then we are able to manipulate it. These images come from an online app through Wolfram Alpha. In the Canvas link, I have linked a fun, similar app you can do online where you're manipulating the shape of a dog, or there's a cat or a mouse, if those are your preferred animals to manipulate with the different matrices. So when we want the horizontal reflection here, T of xy equals negative xy, the reflection on the y-axis. Our corresponding matrix is this negative 1, 0, 0, 1. And that comes from setting up T of basis vector E1 and T of basis vector E2. So T of E1 is going to be T of 1, 0. And that's the negative 1, 0 that we get here in the first column. And then T of 0, 1 is still just 0, 1 because y is unaffected in our horizontal reflection formula here. So that's the 0, 1 we see in the second column. And then similarly for the reflection of the y-axis that we see in this flipped F in the second image. We have the matrix 1, 0, 0, negative 1. So if you want to see how that works out, you know, T of 1, 0 is going to be here still 1, 0. So that corresponds with 1, 0 in the first entry of this matrix. And then the second entry comes from T of 0, 1. So this is 0, 1 is just basis vector E2. And so that's the 0, negative 1 that comes in the second column. Now in this case, because it's such a simple example, you can see because of symmetry, we would have gotten the same result if we put our resultant values in the rows, but that's just a coincidence because if you're working in a higher dimension, you're going to end up with not quite the same symmetry. So make sure you're remembering that the calculations from our linear function T of xy on the basis vectors end up in the columns. And then if we're reflecting about the line y equals x, you can see our matrix here is 0, 1, 1, 0. And if you want to see how the math works out there, the T of 1, 0 is going to flip and be 0, 1. And T of 0, 1 is going to flip and be 1, 0. So when we put those in the matrix, we get 0, 1 in the first column and 1, 0 in the second column. And right here is a visual of what the letter F looks like when it gets flipped around the line y equals x. So you can visualize here's the line y equals x right through, like we put the mirror right there and reflected our letter F around it. Here's some visuals of expansions and contractions. So in this first example, our K is 1.5. So we put a 1.5 in the first entry of the matrix. And you can see here, F is sort of stretched out horizontally by 1.5. And in our second example, K is 2. So that means we've got this vertical expansion of the F. And so here the F is expanded vertically by a factor of 2. So in the app I linked, you can go in and manipulate the dog by changing the matrix just how you like and work through the expansions and contractions and the shears and the reflections. So let's take a look at how the shears would look here. Oh, we've got some horizontal and vertical contraction first. So if you want to contract horizontally, use a K value less than 1. So when K is 0.5, you can see how the grid kind of horizontally contracts there. And then if K is 2/3 here in our vertical contraction, we've got 2/3 in the 2, 2 entering this matrix. And then you can see it's like it got squished together vertically, like we put an accordion there and squished together the letter F. Here's our shears. So in the shears, we have the constant in the corner. In the horizontal shear, the constant's in the upper right corner of the matrix. So here we've got 0.5 up there. So our function T of xy is x plus 0.5 y. And then I should have a comma y over here. And so that's how we got F here. And you can see, oh yeah, it's just like a tilting kind of. So the area hasn't changed, but all of the individual little unit boxes in here are now kind of tilted in the same way that we saw the rectangular shear tilted. And then the vertical shear here, here we're using a 1, so the shear is going to be T of xy equals x y plus 1. And so, or y plus x, that's why y plus 1x. So that's why I didn't change. So here is what the vertical shear looks like there when the shear constant is 1. So this is the formula I typed out here. I just didn't say 1x. Okay, in the next video, we're going to take a look at rotations and we'll work through some examples so that you see how the rotation matrix works.